Hi, let's talk about the work of a force and change theorems. Alrighty, now the work of a force can be given as the integral of force times dr, where r is the position vector and F is the force vector. So suppose I have an object and first, well, you can use the classic billiards analogy, right? You have all different kinds of balls, and I'm gonna only look at the motion of this ball. Oops, there it is. Okay, and I'm going to hit this first with a force of 10 newtons. It's going to go somewhere, get some work done. And from here on, I'm going to hit it again with some other force. And so it's literally the sum of all forces times the the total addition of the position vector that it moves is equal to my work. Now, one important thing to note here is that since work is a scalar quantity, um, it really does not matter since work is a scalar quantity, it really does not matter what path we take. It only matters the distance that we cover. So it does not matter if our ball ends up here or here. It only matters what's the distance, the total distance that it covers. And this sort of makes a lot of the calculations easier for us. Now, now let's look at what this really means. So you're gonna have a path integral, let's say, from vector r1 to vector position vector r2, and you have your force times dr. Now, um, if your applied force is a constant, you can bring this over to the other side, and so you would simply have an integral like this. Now you may ask, what if your applied force is not a constant and there are forces being applied differently throughout different intervals of time or the different intervals of position that they're giving in. And then you might say, oh no, so does that mean that since now work, we have a multivariable function, does that mean that we have to evaluate double integral? Well, not necessarily. You don't have to do this at all, especially since we have not learned double integrals yet. So the way you're most probably going to go about this is you're going to divide up the work integral for the position vector for which the force being applied is constant. So you have a position vector from R1 to R2, and force F1 will is applicable between R1 and R2, and you're gonna sum that up with um, another force value that is applicable between, say, R2 from R3. So we can essentially generalize this as work as being the sum of all forces times the distance upon which that force does work. And that's essentially what you need to know about work. It's pretty much the same that we did in physics in high school, except we're sort of generalizing the approach using calculus and using vector math to represent different components instead of solving everything in terms of resultant motion. We're breaking it up into different components and using vectors and things like that. Looks like I've forgotten the sign over here. Okay, now the work energy theorem states that this work that we have here, the sum of forces times its distance, this should be equal to the change in kinetic energy. So the sum will be equal to 1/2 m v final squared minus 1/2 m v initial squared. And the only thing that changes from high school physics is that here velocity will be a vector. So most likely, when you solve a problem for, I'm not going to solve a specific problem in this video. That will be for next video because for this video, I just like to explain the overall theory of this, and we can apply all of this into practice for the next video where we solve a practice problem. But let me show you what this equation here might actually look like when you get to solve this. So you're gonna have a force and multiply that, scale it with your ijk position vector, and that will be equal to 1/2 mass, and you have a velocity vector over here. So that is um, the derivative of um, j and k vectors squared, and these are all you're gonna take this from the final position, and you're gonna take the derivative to find the initial velocity from the initial position, and in cases where this equals to zero, well, all of the term goes to zero. So let me finish this out for you. Oops. Hold on. Uh-oh. Okay. Initial J dot initial and vector K dot initial. So this is really all it for the theory is pretty simple to be able to convert from work to force. Pretty much all you have to be all you have to remember keep in mind is have a really good understanding of working with vectors, and you should be fine. Okay, let's do some impulse momentum theory. You know that momentum is equal to mass times the velocity, and that F equals ma. Now, to get from momentum to force, you know that the mass is going to stay the same. So pretty much you basically need to get from velocity to acceleration. And you know how to do that. You just take the derivative of momentum with respect to time, and you can change this acceleration vector into the force vectors because dv by dt is essentially acceleration. So, yay. And you can pretty much say the same thing about angular momentum, right? I hope this is the equation as far as I remember. So, you take the derivative of this with respect to time, and you'll essentially get the moment, the moment of inertia. Okay, so now if you have two or more objects, let's say, or let's keep it at two for now, that two objects that collide with each other, you have a case of this being either an elastic, inelastic collision or a perfectly inelastic collision. In an elastic and an inelastic collision, m1 v1 plus m2 v2, that is the mass times the momentums of say block 1 and block 2, um, initial, I'll denote I, will be equal to m1 v1 plus m2 v2 final. And for the inelastic case, so think of it this way: these blocks are gonna bounce off of each other and go off on their own way. You already know that from high school. But in an inelastic collision, in case you forgot, you pretty much have the case where both the blocks stick together and move in one direction. So you're gonna have m1 v1 plus m2 v2 initial is equal to m1 plus m2 times um, v final. So m1 plus, well, you don't need this anyway. Yeah. Yeah, I mean, that is pretty much it. Um, in terms of the theory itself, in terms of the theory itself, the actual dynamics part of it is not as complicated as kinematics because we're not dealing with a new type of coordinates or whatsoever. We're essentially taking the same concepts that we learned in high school and sort of applying it to the new way that we do it with vectors and things like that. And so this is pretty much all the theory that you need to know for particle dynamics, because after the break and after test two, we're going to be doing rigid body dynamics. But for particle dynamics, there's actually not much more to say to this. And if let's take a look at two of the problems on Lihota's web page thing. So I'm not gonna solve this problem in this video, but I'll just briefly talk about it. So so here we have a scenario in which we're gonna have to find let's see, velocity v1. Now, the main idea with this is not to do with the kinematics way, and it'll be really hard. It'll be really unnecessary to do the kinematics way even. But if we define our coordinate system like this, say z, x, y, and we're essentially gonna find everything using the work kinetic energy theorem. So with work, as I said, you have the force vector times the position vector, and you can consider this as your origin point, or yeah, pretty much. And we may actually like we can solve this perhaps next video, and you have to look at what force is essentially doing the work, because you have your motion in two components. You have it in I and J components, and you also have forces acting in two components. You have G that's only acting in the J component, and you have um, ST, the applied force here, that acts in both I and J components. And you're essentially going to resolve these components, resolve everything into I, J, and K, and solve it in vector form like that. And your velocity v1 will be contained in this equation right here, 1 half m vf minus, okay, vf minus v initial, vf squared minus v initial squared. There we go. So yeah, that's pretty much it. And you're already given the initial velocity too. um, just sort of look at which components that initial velocity applies to based on by deriving your position vector, and you'll be able to find the final velocity v1 in no time. So easy peasy lemon squeezy. If we take a look at this problem here, you basically have that uh, momentum impulse theory problem where, and I don't exactly know how I would go about doing this until I actually start doing the problem, but you have a scenario here where between balls 1 and 2, it's perfectly elastic. So the equation of P1 momentum of P2 is equal to P prime 1 plus P prime 2. But then when you have the perfectly plastic collision, you're going to have P2 plus P3 is, well, actually, this will be P prime 2 because you're going to be, the motion of this ball has already affected the motion of this ball. So P prime 2 plus P prime 3 is essentially, you're going to combine the masses of those two blocks times, um, I'm going to say velocity total, and you're asked to find the velocity of ball 3 upon impact. So you first solve this equation, and then you're going to then solve this equation. Well, all right, then I think that is pretty good. Ooh, look at this. Yeah.